All right, everybody, welcome back. Excuse me. In this video, we're going to be talking about information from section 5.7 of AP Calculus using the second derivative test to determine extrema. A few lessons back, we talked about using the first derivative test to determine extrema. Now we're talking about using the second derivative test. And again, we're talking about using it to find local extrema. So we're going to have the first derivative test and the second derivative test as two possible ways that we can find local extrema after today's lesson. So here we go. In the box, you see the second derivative test for local extrema. Notice that both parts of this start with f prime of c being equal to 0. The second derivative test only applies when the derivative here is equal to 0, and we need to know if f double prime of c is less than 0, then there's a local maximum. Now let's look at why that is. If I know at a point that f prime of c is equal to 0, that means that the slope at that point is 0. And if I know that f double prime of c is less than 0, that means that the curve is concave down. And you see an example of that scenario right here on the left, where at this particular point, the derivative value is equal to 0, and at that portion of the curve is concave down. And when we have that situation occur, it must be the case that this point is a local maximum at x equals c. And then we have, similarly, when f double prime of c is less than 0, we have this case. And again, we have the slope being 0 at the point, but then the curve around the point is concave up, which means that that place where the slope is 0 has to be at the bottom of the graph, and therefore we have a local minimum there. So if I'm using the second derivative test for local extrema, I'm going to find the first derivative, see where it's equal to 0, find the second derivative, see what the values of the second derivative are, where the first derivative is 0, and then I can use those to determine whether that point is a maximum or a minimum. All right, when can I use the second derivative test? If f has a critical point at x equals a, and f prime of a equals 0, that's one thing that has to be true. Tangent line to the function must have a slope of 0. It cannot have an undefined slope to use the second derivative test. And then if the second derivative is either positive or negative. If the second derivative is 0, then the second derivative test is inconclusive, and we would need to use another method to see if the function has a maximum or a minimum at a particular point. All right, example 1. Identify where the extreme values of the function y equals x cubed minus 3x squared plus x minus 2 occur, and use the second derivative test to determine if they are maxima or minima. So the first thing I'm going to do is take the derivative of this function, y prime. It's going to be 3x squared minus 6x plus 1. And I'm going to go ahead and take the second derivative a while as well. The second derivative is y double prime equals 6x minus 6. So the first thing I want to do here is I want to figure out where this first derivative is equal to 0. So I'm going to set that function, the derivative, equal to 0, and I'm going to solve this. And I can use the quadratic formula, or I could use my calculator, or I could factor if it's factorable. I don't think this one is factorable. And I think I would probably just be best served in solving this equation. Maybe I'll solve it using my calculator. Like I said, I could use the quadratic formula as well. I'm going to opt to graph it and find the zeros using my calculator to help me out. There's the curve. All right, I need the 0 command. And I get that it is at x equals 0.183503. I'm going to keep a couple of extra digits just so that when I substitute into the second derivative, I get the most accurate answer that I can. And then I'm going to find the other 0. and that occurs at x equals 1.816497, x equals 1.816497. Okay, so those are my possible locations for maxima and minima, because those are the places where the first derivative is equal to 0. What I'm going to do is I'm going to find the value of y double prime at each of these, and that is going to tell me whether or not this is a maximum or a minimum. Okay, so I'm going to find y double prime of 0.183, etc. I'm going to find y double prime of 1.816497 and see what those values are. So my second derivative is the function 6x minus 6. I'm going to see what that is at 0.183503. I get negative 4.899. And I'm going to get the calculator stuff out of the way here. I'm going to do the other point at 1.816497. And that's positive 4.899. Okay, so here the curve is concave down because the second derivative is negative. And knowing that it's concave down means that it's going to look like this. And therefore, so there is a maximum by the second derivative test. Because y double prime is negative. So y double prime of x is less than 0. Okay, this one's concave up because y double prime is positive. If you think about it, if it's concave up, that means we're going to have a minimum there. So there is a minimum by the second derivative test. Because y double prime is greater than 0. And there's the second derivative test in practice. All right, let's keep rolling. We'll go ahead and look at our second example. The second example is from 2007 AP Calculus AB exam. It is question number 6, which means that it is non-calculator. We'll go through the whole process here. Let f be the function defined by f of x equals k times the square root of x minus the natural logarithm of x for x greater than 0, where k is a positive constant. I'm going to be thinking about this function as k times x to the 1/2 power minus the natural log of x. And I'm going to go ahead and take the derivative accordingly. F prime of x is equal to 1/2 times k times x to the negative 1/2 minus 1 over x. Or if you wanted to rewrite that, that's equal to k over 2 square root of x minus 1 over x. Again, or we could simplify it more if we wanted to. I'm good with that as my derivative. And then my second derivative is the derivative of that function, which is going to be negative 1/4 k times x to the negative 3/2 plus 1 over x squared. So that's our derivative and our second derivative. Hopefully you're comfortable enough with derivatives by now that you don't mind that I kind of zoom through that. Part B, for what value of the constant k does f have a critical point at x equals 1? For this value of k, determine whether f has a relative minimum, relative maximum, or neither at x equals 1. Justify your answer. Okay, so in order for it to have a critical point at x equals 1, that means that this derivative here has to be 0 or undefined when x is 1. If I substitute 1 into this function, I get that f prime of 1 is equal to 1/2 k minus 1, because this right here becomes 1/2 k, this right here becomes 1. And so in order for there to be a critical point there, that's got to be equal to 0. And I solve this for k. I get k is equal to 2. And now I want to see, is this going to produce a relative minimum, relative maximum, etc. If I put this k value into the second derivative, then f double prime of x is equal to negative 1/4 times 2, which is negative 1/2, times x to the negative 3/2 plus 1 over x squared, and therefore f double prime of 1 is equal to negative 1/2 plus 1. It's positive. So f has a relative minimum at x equals 1 because f prime of x equals f prime of 1 equals 0, and f double prime of 1 is greater than 0, comma, so it is a min by the second derivative test. So there we've used the second derivative test again. And then we're going to move on to part C. For a certain value of the constant k, the graph of f has a point of inflection on the x-axis. Find this value of k. Okay, so if the graph of f has a point of inflection on the x-axis, there are two things that we know. Okay, that means that the function is equal to 0, and so I set the original function equal to 0. It also tells us, since there's a point of inflection there, that the second derivative of the function has to be equal to 0. And so I set the second derivative equal to 0. Okay, and I can solve for k here. This gives me natural log of x is equal to k times the square root of x, and therefore k is equal to natural log of x over the square root of x. Over here, I'm going to subtract 1 over x squared from both sides. And a little manipulation gives me that k is equal to 4 over the square root of x. So k is equal to both of these things, therefore they are equal to one another. So there we go. This means, since I've got the square root of x in the denominator, I need the numerators to be the same, so I get natural log of x is equal to 4. And therefore, x is equal to e to the 4th power. But I'm not done, because I want the value of k, not the value of x where this happens. And we just said here, k is equal to 4 square root of x. See that right there? So k is equal to 4 over the square root of this x value that we just found, and therefore the value of k, where the graph has a point of inflection on the x-axis, is 4 over e squared. All right, we're going to call it quits there. That's the end of our lesson on using the second derivative test. We focused on it on part B in this free response problem and in our first example, and saw a little bit of extra AP practice to kind of synthesize some things that we've already talked about in this unit. All right, so get yourself some practice on using the second derivative test, and then we will be back in the next set of videos to talk about section 5.8 and talking about sketching graphs of functions and their derivatives. All right, see you then. Have a great rest of your day and enjoy yourself.